So when I consider the energy balance of a plug flow reactor, just when we derive the mole balance, we are going to do it over a small little slice of volume of that reactor, where the change in enthalpy, sum of the change of enthalpy of my flowing streams in that little volume is equal to the amount of heat transfer from that small slice. And the heat transfer can still be calculated as a heat transfer coefficient multiplied by an area, and of course still divided by the volume of the slice. But now that area is the external surface area of that very small slice that we are considering. So we can write that by just using, for a tubular reactor, which is the shape of most reactors, we can write that by considering the external surface area, and that will be the circumference multiplied by the length that I'm considering here, and divided by the volume of that small slice. So here I end up with a parameter A, which is equal to 4 over the diameter of my tube. That gives me the surface area available for heat transfer per reactor volume. So when I now include that in my energy balance and I take the limit where del V goes to 0, that is still A, it's a function of my tube diameter, and I can say that the change in enthalpy per volume in my reactor must be equal to the amount of heat transfer, where I have an area per volume parameter to express that heat transfer. If I want to write that energy balance for a packed bed reactor, so where I want to use my mass as my independent variable, make sure that you can see why you then need to divide that term by the bed density in your reactor. So once again, the enthalpy of my flowing streams, the total enthalpy, will change due to two effects. Because there's a change in temperature, I'm going to consider the molar flow rate to be constant in that slice when I change the temperature, and it is going to change because there is a change in the composition, and that is accounted for by the heat of reaction. And once again, I'm going to use my extent of reaction. What is the extent of reaction J for each of the reactions in that small slice that I'm considering, multiplied by each of the heats of reactions of all my reactions J. So once again, I'm going to use my definition for the extent of reaction, as you did in Smith, Van Ness and Abbott, to relate the extent of each reaction J to a change of a specific component as a result of that reaction J divided by the stoichiometric coefficient of that component in that reaction J. And we are further going to, so we can now substitute that into our energy balance. So then we just have molar flow rates and stoichiometric coefficients in there. And if we now inspect that, we realize that this dFij dV term is simply equal to the rate at which component I participates in reaction J. So for each of the reactions, I need to consider a single rate term and divide by that stoichiometric coefficient of the specific component that I used as the basis to perform my energy balance. So after substitution, and this is the shape that you used in that extensive TUT where we had the multiple reactions, we had to account for each heat of reaction. This is the shape of my energy balance, and I am going to manipulate it so that I have the differential equation dt dv as the subject of that equation, because we want to integrate numerically over that volume range of my reactor and see how the temperature is changing. Of course, the rate of the reaction will be a function of temperature and composition at each point as I integrate through my reactor. So once I make this dt dv the subject, this is the shape of my energy balance over a plug flow reactor where I have multiple reactions taking place. And once again, I can calculate this del H reaction at the temperature of the slice by considering the del Cp reaction as explained in the slides on the CSTR. So for a specific case of an adiabatic PFR, the U times small a term becomes 0. and this is the remainder of my energy balance. And we are going to simplify this by looking at a single reaction taking place in my PBR reactor. The specific reaction we are going to consider as an example is the one where reactant A is converted to products, and we are going to base our rate in that reaction based on the conversion of A. So the rate of A in that reaction is what we will consider. From our mole balance, you should be able to prove that the rate can be expressed as a function of the inlet molar flow rate and this dx dv. Make sure that you can end up with that differential equation of the rate from your mole balance. Do some CKN revision. And we know that the stoichiometric coefficient of A in that reaction is equal to -1. So now, after substitution, we end up with the differential equation where I have the change in slope, or the slope of dt dv is equal to the slope of dx dv. It's directly proportional to that slope, and this is the parameter that connects the two slopes. For a reactor where we had x is equal to 0 at the inlet, so if I integrate now from T0 to temperature at any point in the reactor, and x goes from x is 0 to x at any point in the reactor, I can prove that I can once again get a linear expression for temperature as a function of x. And that is of course provided that del Cp of the reaction was pretty much equal to 0, and that del H of the reaction as I integrate is not a function of temperature. But this equation, if you perform the energy balance for a CSTR reactor, you will see that I have exactly the same linear relationship of temperature as a function of conversion. So what that implies is in my plug flow reactor, instead of having a differential equation for my energy balance, if all the conditions I mentioned here is true, it is adiabatic, so I don't have the path variable Q in my energy balance. I have a del Cp reaction is equal to 0. I can have an algebraic equation that represents my energy balance of temperature as a function of x. For each little slice, I can calculate the temperature algebraically as I integrate. Still, I have to integrate over x with a change in volume. So if I now consider the non-adiabatic plug flow reactor, it's important to realize that I cannot now get a straight line relationship between x, even for a single reaction, between x and temperature. And that is because Q is a path variable, the rate of heat transfer at each position in my plug flow reactor. At each position, because I have a temperature variance over the length of my reactor, the rate of heat transfer at that specific slice or in that specific slice will be a function of the temperature in that specific slice. So there's no possibility of getting a straight line relationship, and when I have a non-adiabatic PBR, I must use the differential equation for change in temperature with volume to express my energy balance. It is still possible, however, to calculate the total amount of heat transferred in kilowatts, like Aspen would do it, by considering flow, enthalpy in, flow, enthalpy out, and I can get an answer for Q, the total amount of heat that was flowing from that reactor as a kilowatt or a megawatt value. However, what I must realize is that this rate of heat transfer I can actually draw as a function of my volume along the volume of my reactor. So at each little step I will have a different rate, but the total here will still be equal to the total amount of heat transfer due to an overall change in enthalpy from the inlet to the outlet state.